Hello, everybody. Here is David Odelli. I'm a PhD student of the Federal University of Viçosa in Brazil. And today I'm going to talk to you about my research project, which represents a collaboration with a technical university of Denmark, where my co-advisor Federico Casanova is professor. And in particular, my project regards the interaction between fish skin gelatin and pea protein at the air-water interface after ultrasound treatment. So here I've summed up a bit what are the contents of my presentation today, and I will first have a brief introduction of what is it an air-water interface, focusing in particular on the foam system. Then I will explain which were the materials and methods that were used for doing my research, before to present the results and the conclusion and perspective for the future of this study. So first of all, when we think about an air-water interface, the most classical example is given by a foam. In fact, we should know that many food products are based on foam system or contain foam as an ingredient, like for example, beer, souffle, or meringue. They're all described as foam. In fact, a foam system can be described as a two-phase system in which gas bubbles, normally air, are trapped into a continuous phase, which could be liquid or solid. Also, this foam system, they contain some molecules, some called surfactants, that are able to react with both of the phases and stabilizing the overall system. And usually food foams contains dairy and egg proteins thanks to their high efficiency in stabilizing the system. However, recently new and more sustainable sources of protein have been evaluated. Like for example, a previous study used fish gelatin obtained from the byproduct of fishery industry as a foaming agent, and tried also to improve their functional properties by applying ultrasound treatment. In my study, I continued the evaluation with this kind of protein, but I also added pea protein isolates as a new source of foaming agents. So the objective of my studies were in particular to reply to these three questions, and how fish gelatin and pea protein behave at the air-water interface, and if an ultrasound treatment is able to improve the foaming properties of this protein, and in the end, if there is an interaction when fish gelatin and pea proteins are combined. To reply to these questions, I started from both the powders of both the proteins, and I created three different solutions for three different particle suspensions with three different ratios: 100% fish skin gelatin, 100% pea protein isolate, and a mixture of 50-50% ratio of them. And all the solutions were then standardized at a concentration of 18 grams per liter into a neutral pH, and were then submitted to an high-intensity ultrasound treatment for 5 minutes at a power of 275 watts. The methods used for the research started with the characterization of the powders, which have been done by their thermal properties by DSC, for their protein content by Dumas method, and their elements contents were all already characterized by a previous study on the same proteins, on the same powders that I reported here. My research started with their particle suspension or their solution of these powders, where I characterized their particle size by dynamic light scattering and SEC-mods, their interfacial properties by pendant drop, and their viscosity and rheology by rheometry. And soon after this, I foamed them. I foamed all of the solutions with a mechanical agitation using an ultra-2rax instruments, and I evaluated their foaming properties by a visual analysis coupled with a turboscan tower instrument, and I also evaluated the foam microstructure with a confocal laser scanning microscopy. So let's dip into the results now, and the first graph here presented regards the particle size of the particle suspensions, and here we can make the first consideration is that pea protein has a way larger size than fish gelatin. And also, when the proteins were mixed, the results showed a really similar behavior to the protein only for the mixed samples, as if the instrument only detected the P protein in the mixture of proteins. The second consideration that can be done is that the ultrasound treatment only reduced the size of P protein as well as the mixed proteins, while slightly increased the sizes of fish gelatin, as if there were better intermolecular interactions. From these other graphs, we can see the zeta potential of the particles, thus their charges, and we can say that all of the particles presented negative charges, while once again, P protein had a way higher negative charge than the fish gelatin, which is close to neutral. And the ultrasound treatment intensified these charges for the P protein and the mixed proteins, while didn't affect significantly the fish gelatin. To continue the evaluation of the particle sizes, we also use a different approach, which was the size exclusion chromatography, also known as SECMALS. And from the results that are listed here in this table, we can see that both the PPI protein and the mixed proteins were composed of 4 different fractions, while the fish gelatin protein were composed on only 1 fraction. And also, we can say that the ultrasound treatment did occur with some modifications. Like, for example, it reduced the molecular weight of the fraction 1 of both fish gelatin and P protein, while increased the molecular weight of all of the other fraction of P protein and the mixed proteins. Another consideration that can be done is that the mixed proteins, when they were mixed, presented higher molecular weight of the particle sizes, and therefore make us suggest that when they were mixed, there has been an interaction between these 2 proteins. Here are the graphs of the interfacial tension of all the solution. The interfacial tension values were recorded for 1,000 seconds by an optical instrument, which calculated the values based on the shape of a small droplet, of a small drop of all the solutions. And in particular, in general, we can say that the lower the interfacial tension value and the higher is the stability and the interface of these surfactants. And here we can see that the lowest values were reached when the proteins were mixed, while the higher values were reached with the fish gelatin protein. Another consideration is that the ultrasound treatment only modified the values of the interfacial tension values of the fish skin gelatin, improving them, reducing the overall values, while there hasn't been a significant difference for both the P protein and for the mixed proteins. In this graph is represented the viscosity, the apparent viscosity of all the solutions, and are represented as a shear stress over the shear rate. And the data were collected using the power law model, and all of the solution exhibited a Newtonian flow behavior, where N, the flow behavior index here, is close to 1. And as we can see from the second equation here represented, in this case, the consistency coefficient M is equal to the apparent viscosity. And all of the solution presented a range of viscosity between 1 and 1.5 millipascal over second. And we can say that the ultrasound treatment in particular reduced the viscosity of both the fish gelatin and P protein, while didn't affect significantly the mix when the proteins were mixed. Now let's dip into the characterization of the foams. To do this, we focused on the foaming properties, which are described by 3 different equations that give us an overall idea of the quality of the foam and the stability of the system. The first equation considered is the foam capacity, which can be described as the diffraction of air into the foam. And here is described as the difference between the foam volume and the initial solution volume over the foam volume in percentage. And here are represented the graphs, the results of all the solutions of the foam. And we can say that in general, all of the foams reached a foam capacity value of around 50%. The only exception was the fish skin gelatin, the untreated fish skin gelatin, which happened with values of 46% of foam capacity. And the ultrasound treatment only improved this sample in particular, increasing the values of foam capacities, while it didn't affect both the pea protein and the mix, and when they were mixed. The second equation considered is the foam stability, which gives us an idea of the stability, the overall stability of the system, and is described as the volume of the foam at different period of time over the volume of the initial solution in percentage. It was considered a period of time of 90 minutes where all the foams of the samples were visually analyzed, evaluated. And as we can see here from these graphs, in particular, the pea protein and the mixed foams presented really high stability over the period considered of 90 minutes, with the mixed values which were higher than the rest of the samples. While fish gelatin presented a steadily decrease of foam stability values over the overall period considered, until reaching values below 10%. And also another consideration is that the ultrasound treatment only improved the values of foam stability during the first 25-30 minutes. And after this period, the values dropped below the controlled. The third and last equation considered is the liquid fraction, which consider the air, the water trapped into the foam, and therefore gives us an idea of the ability of the proteins to retain this water and stabilizing the overall system. And here he is described as the initial volume of the solution as a difference of this volume with the volume of the drainage liquid over the volume of the initial solution in percentage. And here are the results. As expected, all of the samples presented over the 90 minutes considered a tendency to 0% of the values. It was expected because the liquid is going to drain because of gravitational forces during time, with the time. And we can say that the sonication only improved here, as we can see from the results, when the proteins were mixed, while didn't affect significantly all of the other samples, like the single proteins. Immediately after the foaming process, the foam were also loaded into a tube like this with a 55 millimeters high, and the two phases separation occurred, where here in blue we can see the liquid drainage, and in orange the foam at the top of it. And these kind of tube were then loaded into the turboscan instrument, and a graph like this was obtained. Where the backscattering values of a beam of light was analyzed over a period of time of 90 minutes, here represented with different colors, over the overall height of the tube. Now we can say that the backscattering values are given by the air bubbles of the foams. Therefore, how these values modifies, how it changes over the time, we can have an evaluation of the changing on the foam over the time. And in these graphs in particular, we can see that two main effects occurred. The first one is the drainage of the liquid at the bottom, which makes the backscattering values shift to the height, to the top of the tube. And the second effect that occurred is the coalescence of the bubbles, which unite and the burst, making the peak of backscattering reducing in value. And now the backscattering values are important because thanks to the mean theory, knowing the volume fraction of air, which is our phone capacity described before, and knowing both the refractive index of the dispersed phase and the continuous phase, we can calculate how the mean diameter of the bubbles of each foams and how they change during the time, allowing us to create a graph like this, where we can see the difference in the bubble diameters of the foams over the 90 minutes considered. Here, from these results, we can conclude that both the mixed proteins and the P proteins steadily increase their bubble diameter, but overall maintain a really good stability over the 90 minutes considered. While it wasn't the same for the fish gelatin foams, because their air bubbles increased rapidly until they reached a limit and burst around 25-30 minutes. And another consideration is that the sonication didn't improve the stability of the bubbles, but instead the bubbles burst even earlier than the control. Now, at last, the foams were then visualized by confocal laser scanning microscopy to evaluate the foam microstructure, and movies of all the foams were recorded, like this one, where we can see the two phases, the air and the liquid, and the protein layer. The proteins here were labeled with rhodamine B, and here we can see clearly the fluorescent layer around each air bubbles that is responsible for the stabilization of the overall system. To be sure that this layer was made of proteins, we also compared it with general soap foam, and here we can see from the bottom right peak image that there is not this fluorescent protein layer. And movies like this one were recorded, where we can clearly see the proteins particles interacting between them at the interface of the two phases. And after this, all of the images of all the foams of all the sample were compared between them to try to find a difference between them. But first of all, the fish gelatin foams were excluded from this kind of valuation because they drained too much liquid, and it was almost impossible to visualize them by the instrument. So we did only a comparison between the P protein and the mixed samples, but unfortunately, no significant difference were obtained here. So as the conclusion, we can say that the specific ultrasound treatment used here of 5 minutes for 275 watts didn't show a significant difference on the behavior of all the proteins considered at the air-water interface. However, when the proteins were mixed, they presented the most encouraging behavior at the air-water interface, making us suggesting the hypothesis that the fish gelatin and P protein could have developed a weak interaction between them. However, to further analyze and study this kind of interaction between these two proteins are necessary different studies. For example, for the future, we can also include evaluation with the ellipsometry and surface rheology, which could be really promising in this context. Like for the perspective of the future, we can say that since various reports forecast that the global food hydrocolloids market will increase, new research are for sure needed to evaluate alternative sources and also to improve the hydrocolloids applicability. And as we saw from this study, fish gelatin and P protein represent a good potential of hydrocolloid sources, thanks to their characteristics, thanks to their ability to interact with both of with different phases. And these biomolecules, as well as other biomolecules derived from byproducts, both of the food and feed industry, can in fact increase profits of the processing industry and can also reduce the environmental pollution at the same time. And also some physicochemical modifications, such as the ultrasound treatment, can be employed to further improve their application and their functional properties. This was the end of the presentation. If you have any question, just feel free to ask me. Thanks for your attention.